Okay, your next assignment is due on Wednesday, the 2nd of February. That's available now on Blackboard. It's exclusively problems related to what we're going to go over in today's class. So you're going to learn today enough that you could do all 3 of the problems that's due on Wednesday of next week. On Friday of this week, we're going to have more practice of this 3 reservoirs problem. This is kind of a classic problem in hydraulics. And of the YouTube lectures that I post, it's always interesting to me to see what gets the most views, because I can kind of tell what other topics are being taught across the world and what other topics people are interested in learning about. My 3 reservoir videos get a lot of views. So that tells me that people all over are learning this, not just us. So any announcement related questions before we dig into the 3 reservoirs problem? No? All right. So here's the scenario. There are 3 tanks that are connected together with pipes. And each one of the tanks have a different reservoir elevation. There's one reservoir here, tank B, where the water level is high, another one where the water level is low, and then a reservoir in the middle. And it's that middle reservoir that makes things tricky, because the high and the low, it's pretty easy to guess what direction the flow is going to be in pipe BD, for example. So consider pipe BD. Is the water going to be flowing into this reservoir or out of the reservoir? Well, since it's the highest in elevation, the driving force is going to be out of reservoir B. So we can just know from inspection the flow direction through pipe BD and the flow direction for pipe DC. Now, location D is just simply a junction. That's where the water flow comes together from the 3 pipes at this junction. But the 3 reservoir problem, our big uncertainty is what's happening to the middle reservoir. Is the water going in or going out of the middle reservoir? Now, let me ask you to reach back into your memory. Do you remember when we've talked about, instead of describing the pressure at a location, we've sometimes talked about the head at the location. Do you remember what that means? Like, how is the head at D different from the pressure at D? In terms of length, good. That's a great start. We're off to a great start. So it would have units of length, so feet, for example. It's a way of expressing the energy as a distance. And so remember the 3 terms of the energy equation. Energy can be in the pressure, the elevation, and the velocity. Those are, when we've got water flowing through pipes, those are the 3 locations the energy can be. So what we're saying is let's add it all up. And if we add up all of the energy, and we're doing this in units of length, which is what we'll get here, the total energy at D, there's some amount of head there. And most of the head is going to be as pressure. I guess it depends on what we use as our elevation reference, right? But if the head at D is higher than the water surface elevation at A, then what would that tell us about the flow direction? So if the head at D is greater than the water surface elevation at A, then flow, fill in the blank. What's happening with the flow if there's more head at D than the water surface elevation at A? What direction will the water go? It'll flow into A. So that'll be the driving force. Water's going to go from D towards A if there's more head at D. And so the opposite of that is if the head, if the head at D is less than the water surface elevation of A, then flow out of A. Whereas before it was flow is into A. So think about the driving force. The reason why we knew the water's going from B towards C is because B has the highest elevation. Water flows from high energy towards low energy. So think about a horizontal pipe. Water flows from high pressure to low pressure. So it all depends, this flow through pipe AD all depends on a comparison of the head at D to the head at A. And the head is just going to be elevation in a water tank, because like at the top of the water here, there's no pressure and there's no velocity. So that's why I was saying water surface elevation of A, because in tank A, all of the head is as its Z, the elevation. Everybody with me so far? Any questions? So this is the 3 reservoir problem. Now, what's been the tricky thing about our using the Darcy-Weisbach equation? When I say Darcy-Weisbach equation, what I mean is H sub F is FL V² divided by D2G. So like we've had a couple of examples so far where it was tricky for us to use this formula. And why?
Because F is dependent on V.
Because F is dependent on V. And here, we don't know what the flow rate is going to be through any of these pipes. We know what is the water elevation, but the 3 reservoirs problem is what is Q. So we don't know the flow rate. That means we don't know the velocity. And if we don't know the velocity, we don't know the friction factor. So we're in one of these chicken and the egg scenarios. And so what have we done before when we were in a chicken and the egg scenario where we don't know F and we don't know V? We started with a guess. So we're going to do the same thing today. We'll start with a guess. We'll see, well, what if the F value is something? Then where does that leave us? So we're going to go through an iteration process today, and after a couple of iterations, we'll converge on a solution. So the problem we're trying to solve is what direction is the water flowing and at what flow rate, how much through each pipe. And then, just for fun, we can also calculate the pressure at the junction, D, if we know its elevation. So that's what we're going to do through an example. We work with that template file that's on Blackboard. Now, our process is that we know water goes out of the highest reservoir into the lowest reservoir, but that middle reservoir we're not so sure about. So how much the flow rate is going to be depends on the driving force. It's the difference in head between the origin and the destination. So we can use that as a general rule in the same way where we have a horizontal pipe. It's the change in pressure, the difference in energy between 2 points that's driving the flow. If you have a big pressure drop, the flow rate will go quickly. If you have a low pressure drop, then the flow rate is more modest. So we use the Darcy-Weisbach equation to estimate the head loss, but the velocity is unknown, and the friction factor is a function of the velocity. So a big part of our process today when we're solving things is using the continuity equation. Anybody remember what I mean by the continuity equation? I used that phrase a couple of times in fluid mechanics. What is continuity equation? I'll give you a hint. It won't be a helpful hint. It was in chapter 5 that we talked about the continuity equation.
Is that flow in equals flow out?
Flow in equals flow out. Very good. And I heard someone else was going to jump in there too. So think about junction D. So what would continuity applied to junction D? It's just we got to make sure that flow in and flow out is balanced. So let's say, for example, the water's going from A towards D. So then what we would say is if the water is going from A to D, we'd say QBD plus QAD equals QDC. So the flow into junction D equals the flow out of junction D. That's another tool in our arsenal. We've got some tools we're going to use, and continuity is an important one today. So that's the foundation. Everybody understand what the problem is, why it's a problem, what the tricks are going to be, how we're going to start with a guess of the F value. We're going to check to know if we're converged, like our convergence criteria is the F value stabilized? Does flow in equal flow out? If those are all thumbs ups, then we'll know we may have a correct solution. That's what we're going to be looking for. This is an iterative process. We're going to use this definition of head. Our head loss due to pipe friction is the Darcy-Weisbach method. Now, the head at D is how much head there is at A minus the head loss. So this formula here presumes that the water is going from A towards D. So this minus sign, this is really important, this part. The head at D is however much head there is at A. Remember, head is energy. The energy at D is the energy at A minus the losses. And it's a minus because of the direction of flow. Now think about, why is there a plus here? Plus. Okay, so the head at D is the head at C plus the head loss. So why was it a plus for this one, but a minus for that one? Well, it's because of flow direction. Going from D to A, we're going against the flow. So that's why it's minus, is there's going to be less energy at D than there was at A. But there's more energy at D than there is at C. So the head at D is however much energy there is at C plus the energy loss due to pipe friction. So you need to be able to have, see a new problem and come up with these on your own. These won't always be given. These, head relationships. So we're going to start by guessing a head at D, and based on the guess, we'll find the head loss in terms of F and V. We're going to assume an F value for the first one, or for subsequent iterations, we'll update based on the most recently calculated F value. And we'll find out what is the velocity. Then we're going to calculate the Reynolds number for the velocity based on our formula for Reynolds number. Then with this Reynolds number and velocity, we can calculate the friction factor with the Jane equation rather than starting with an assumption. And then we're going to calculate the flow rate through the pipe using the continuity equation, and then we're going to balance the in versus the out at junction D. This is the process that's built into the format of the template. I made the template after reading through the book, and the book kind of explained the calculation procedure, and so in my mind I thought, okay, what order would we need to calculate things on a spreadsheet? So I came up with a template based on the procedure that's described in the book. Now, we know that our guess was too high if the flow out is greater than the flow in. So that would mean for subsequent iterations we need to lower our guess of H sub D. But if Q out is greater than Q in, then that means we need to raise our guess of H sub D. So we're going to kind of keep this at the ready. If you've got your notes printed out, it'll be useful to have the notes on one side and the spreadsheet on the other when it comes to this if-then. We may refer back to this slide to help us diagnose whether we need to raise or lower the guess for H sub D. And eventually we're going to get to the point where our flow out and flow in are balanced, and as long as our F values are converged, once we have achieved balance and continuity, then that means that the problem is done because we've achieved convergence. Boy, this sure sounds complicated, but it's really not. You're going to get the hang of it quick. Okay, so here's the particulars. 3 reservoirs, we've got the elevations. We know the lengths of the pipes. We know what it's made out of. Here's one that's cast iron, another one that's cast iron, and one that's galvanized iron. We've got the diameters. So we're just going to solve this 3 reservoirs problem and find out what's the flow rate through each pipe, and then what's the pressure at D. Those are the things we're going to solve. Our kinematic viscosity of water in traditional units is provided, and the physical elevation at junction D is 85 feet. We'll need this to calculate the pressure. You don't need the physical elevation at D if you're not calculating the pressure. We could find the flow rate at D without knowing its physical elevation. But to calculate the pressure, we have to know the physical elevation. So here's our procedure again. Let's open up that template file. All right. Here it is. We've got the diagram. We've got the Jane equation. Look at how I've rearranged the head loss equation to solve for velocity. We're going to use that when we're calculating the velocity based on a known head loss. Here's the kinematic viscosity of water in traditional units. Okay, so our three lines, there's line AD, there's line BD, and line DC. Okay, so if you're following along, key all of that in. The material, it's cast iron for AD and BD, and then pipe DC is galvanized iron. And the reason why we need to distinguish between them is that they have different K sub S values. The K sub S for the cast iron is 0.00085. So I'll drag that down to the next one as well. And then galvanized iron is a little bit more smooth. It's 0.00050. Okay. The lengths of the pipes we can get from the diagram there, 750 for AD, 1,000 for pipe BD, and 500 for DC. Just filling in this given data here. 12 inches is the diameter for BD, 8 inches for AD, and 8 inches for DC. So we'll put in the diameter. You'll notice it's in units of feet. So that is 8/12 for pipe AD, 1 foot diameter for BD, and 8/12 of a foot for pipe DC. How are we going to calculate area? Pi d squared divided by 4. Okay, so pi, pi, open, close parentheses, times the diameter squared, and then divide by 4. Okay. So we can drag that area formula down. Okay, now, our guess, this is the first part where we're in step 1. You can see across the top there, I've got the steps labeled. So step 1, we have to make an assumption about what is the head at D. Our book suggests to assume that the head at D is equal to the elevation of the middle pipe, the middle reservoir. But I think it's a little bit better to not make it that. Things will make more sense if we assume that it's just like 1 foot higher or lower, rather than assuming the same. So I'm going to suggest, let's start with a guess of 111 feet as our guess head at D. And so these other ones, I'm just going to say equals and refer to the cell above it. Rather than type that in 3 times, I'm just using this as a relative reference of the cell above it. All right. So if this is the head, then what is the head loss through the pipe? Now, we're not calculating this with the Darcy-Weisbach equation. This is where we're applying these formulas. Okay, so what that means is, okay, so if the head is 111 at D, then the head loss through the pipe is 120 minus 111. That would say that there is 9 feet of head loss, right? So I'll say the head loss through the pipe is the water surface elevation at A, 120, minus that. AD. No, I'm sorry. Here's pipe A. Here's reservoir A. I was looking at the wrong one. So AD isn't 9. It's... So what's the head loss if if there's 111 here. So it would be 111 minus 110. So if we're assuming that it's 111 is the head at D, then that means we're assuming the water goes from D towards A, because there's more energy at D than at A. Okay, so it would be 111 minus the elevation of the water at A, which is 110. There we go. That's more like it. Okay, now BD, 120 minus our guess, and then if there's 70 at C and 111 at D, then it's going to be 111 minus 70. Okay, so we've got all of our head losses based on the guess. So this is still step one, because all of this is based on what is our guess of how much energy there is at D. All right, so what was step two? Because it's not on the spreadsheet. Find equations for head loss in terms of F and V. All right, well, here they are. Here's the equations of head loss in terms of F and V. I think in your homework on problem 3, I asked you to use the Hazen-Williams equation for problem 3. So the Hazen-Williams equation is also available. You can have a formula that's based on velocity and head loss. But we're using the Darcy-Weisbach, so this is the one we're going to use. Okay, so step 3. What would be the F value? Well, we have to start with a guess right now, because you'll notice that we don't know what is the V, and so we can't start with a calculation of the F value. So let's just pick somewhere in the middle, 0.02 as the F value for these pipes. Okay, so if it's 0.02, then what would be the velocity? This is where now we're going to use this formula. So it is the square root, you see the square root symbol there, of the h sub f times the diameter times 2 times g divided by the F value. Now, my formula is I can't click on the location because the formula is over the cell, so I'll just type in I-27, that's where the F value is, times the length of the pipe. Okay, so I have just solved for the velocity based on our guess h sub f and based on our guess F value. Boy, there's two guesses. Oh, thank you. Yes, it should. What an amateur mistake that is. 32.2. Thank you. Okay. What did I forget? Oh, I'm missing a clothes parentheses here at the end because we had the square root going on. All right. So 1.69 is the velocity if the head at D is 111 and if the F value is 0.02. Both of those things are going to be changed. So that's not the actual velocity, but it's based on a guess. You can drag the formula down to the other two pipes. And now we're going to calculate a Reynolds number based on that velocity, based on the pipe diameter, based on this kinematic viscosity. So Reynolds number is velocity times the diameter divided by the kinematic viscosity. 1.22 E minus 5. Okay, I can drag that formula down. Now that I have a velocity and a Reynolds number, I'm going to use the Jane equation to calculate an updated F value. That's step 6, is update your F value and then update your velocity. Okay, so let's type in the Jane equation. We only have to do it once, fortunately. 1.325 divided by, parentheses, the natural log, parentheses, of K sub s. Make sure it's in units of feet, so it is, that's good. divided by 3.7 times D. So we've got the first part of the Jane equation. This is the relative roughness term. Now we're going to add in the flow condition term. So 5.74 divided by the Reynolds number. Once again, my formula is in the way. I can't click on the cell, so I have to type it in. K27 to the power of 0.9. And then all of that is squared after I close the parentheses. Boy, in the back, you probably can't see any of that formula from the back, right? You need to start bringing a binoculars. You can see it? Wow. All right. Well, if you can't see what I've typed in, at least you can see the formula. So here's let's see, our initial guess of F value is 0.02. Our updated guess, based on the Jane equation, we're okay. It's relatively close, you know. Let's drag this down to the other pipes. And now we can update our calculation of velocity again. So it is the square root of h sub f times d times 2 times g, and of course g is 32.2, divided by f, and we mean this updated f value that we just barely calculated. So that's the one that's in cell L27, okay, times the pipe length. And then close that parentheses and the other one for the square root. Okay, so this is giving us an updated, adjusted velocity. Our initial guess was 1.69. This updated velocity is 1.56. We can drag it down through the other pipes. Boy, the water's really moving fast through pipe DC. Look at that. 13.63 feet per second. That's fast. And that's just all based on a guess of how much head there is at D. We're going to have to adjust our guess. Now, let's think about what this means about flow direction. So compared to the junction, is the water flowing into the junction or out of the junction through the pipe? Okay, so pipe BD. That one's obvious. The water is flowing into the junction through pipe BD. So into the junction from BD. Okay, what about pipe AD? Is the water going into the junction or out? Well, if the head is 111, so our initial guess, see this arrow? If the head is 111, we're saying that the water's going this way for this first round of iterations. So the water is out of junction for pipe AD, and it's also out of the junction towards reservoir C. The flow rate is the velocity times the area. So velocity times the area gives us the flow rate for each pipe. And then down here at the bottom is where we're going to do the flow in minus the flow out. So I guess here I'm suggesting out minus in. We're looking for the difference for continuity. So let's have equals this outflow plus this outflow minus the inflow. So the sum of the out minus the inflow. So how much error do we have in continuity right now? It's 1.05 cubic feet per second. So back to this slide. If the flow out is greater than the flow in, that means that your initial guess was too high and you should lower it. So look what this is saying. This is saying that for the guess that we have, if the head is 111, then you'd have a lot of flow going out, but not very much flow going into the junction. And that doesn't work. That's not what it's going to be. That just is an indication that our guess was too high. So we're going to start with a lower guess. In the next round, we're going to start a guess of 109 feet, a lower guess of the head loss, of the head at D. Okay, so any questions so far on this first junction? I'm going to pause for a second, circulate around, and if you have a... So why is the water going from D towards A in this first iteration? It's because our first iteration said, let's just say, as a hypothetical, that there's 111 feet of energy at D. So if there's 111 feet at D, then the water is going to go from D towards A, because the water elevation at A is only 110. So the water will go from where it's 111 towards where it's 110. So that's why the flow AD is out of the junction, is because of what our initial guess was. Okay, in the next iteration, we can copy all of this stuff. We don't have to type that in again. So just highlight that and copy it. So copy and paste. That's nice. And our initial guess was too high because out minus in was positive. So let's use a lower guess. How much lower? I don't know, 50 feet. Let's just use 109. See where that takes us. 109 feet. And then I'll just have all of them is based on the guess of 109. I think what we're going to be able to do is, except for this head loss through the pipe, we'll be able to copy and paste a lot of the formulas. But we can't just copy and paste this one because the flow direction is going to be different for AD. Now remember, iteration 1 was saying it's a 111, but iteration 2 is saying the head at D is 109. If the head at D is 109, this arrow changes direction. It's the flow direction is this if the head is 109, because the water would go from where it's 110 towards where it's 109. So this is all saying, what if the head is 109? So then the head loss would be, for AD, it would be 110 minus that. For BD, it's 120 minus the elevation at the head at D. And then DC is the guess of 109 minus the water elevation of 70. Okay, so this is like if the head of the water at D is 109, then this is how much head loss there's going to be through the pipes. Okay, now we're not going to do a guess for this iteration. Let's erase that word guess, because it's actually the F value from the previous step. So let's have it be referencing these F values from the previous iteration. Instead of starting over with just a completely new guess, we can do better than that. Let's use the most recently calculated F value. Okay, and drag that down. So that's better than starting from scratch with 0.2 again, 0.02. Okay, let's see, on this velocity, I think we're going to be able to just copy and paste this formula for velocity. So copy the whole thing for velocity, Control C, Control V. All right, so we've got a new set of velocities. Reynolds number, we can copy, Control C, and paste, Control V. All right, great. We've got newly updated Reynolds number. This F value is where we calculate it. It's like our updated F value based on the Jane equation. And once again, we can just copy and paste the F value. And it gives us, the change is more subtle this time. You know, last time there was a relatively big jump for pipe AD, smaller. in the second iteration. That's a good sign that the F values aren't changing as much. I like that. Let's copy and paste these velocities, because the velocity is just based on the this formula again, the rearranged Darcy-Weisbach equation. So we can copy and paste that. Now this flow direction thing we have to diagnose manually. All right. So if the head is 109, then it's flowing from A towards D. So it's in for AD. In BD, the water is flowing in from B towards D. So it's into the junction. And then it's flowing out of the junction towards C. So DC is out. Okay, flow rate is just Q times A. So I'm going to copy and paste again. Control C, Control V. Oh, I missed one. Okay, and then we're going to add up the outflows minus the inflow. So equals the outflow minus both of the inflows. Okay. Since that's negative, look at this rule. If Q out is greater than Q in, then raise the guess of H sub D. So it's negative, which means that our guess for H sub D was too low. So we'll raise it. We'll try 109.5 for this next one. But we're getting closer, right? The error was bigger in our last iteration. The error is getting smaller now. Okay, so let's do this. Wild and crazy. Highlight all of it. For this next copy-paste, highlight all of it. Okay, and copy, and then paste it into the appropriate spot for iteration 3. Just paste. Okay, but what we're going to do is we're going to change the H sub D. Instead of 109, let's try 109.5. Ooh, that's looking better. Look, the error is smaller than it was before. Why couldn't we just change it here? Well, it's because we're still iterating the F value a little bit. So once the F value is good and stable, then we could change the H sub D within the iteration. But until the F value has stabilized, it's better if we don't. It's not changing much for two of the pipes. Look, DC, the F value guess, and the output F value is the same. Also for BD. But pipe AD, there's still a subtle change. It's pretty small, the change in F value. So we're in the iteration 4, I think we're going to get pretty good. Okay, but look, it's negative, which means we need to raise it again. So what's the conclusion? Again, the conclusion is our guess for HD is too low. Raise it. Let's split the difference again. Let's say 109.75. And so again, copy everything. Control C, Control V to paste. And instead of 109.5, let's do 109.75. Okay, that's pretty small. Now let's look at what's going on with the F value. Not a lot of change. Let's use what-if analysis to get us the rest of the way there. Goal seek. So you may remember what we want is our goal is for this to be 0. And so we're going to tell it change this until the difference is 0. Okay, so I'm going to go here to the Data tab, Data, What-if analysis, Goal seek. Okay, so set this cell to a value of 0 by changing this guess of H sub D. And luckily I have the other elevations that are referencing this original. So when it changes this one, it's also going to update the other ones too. So go. Okay. Looks like, boy, for a second there I was worried it wasn't going to converge. It was spazzing all over the place. but it got there in the end. So it suggests that the elevation for the head at D is 109.879. And I mean, if I was really feeling picky, I'd maybe go for an iteration 5 so that the F value wasn't changing anymore. But just for simplicity, we've only got 4 minutes left. Let's leave it here for today, and we'll calculate the pressure at junction D when we gather on Friday. Are there any questions about this spreadsheet? If you have an individual, like a problem on your spreadsheet, and you want me to help you find the error, let me know. I've got a few minutes after class, or you can bring it up on Teams. We can do the screen sharing thing. If you are an early bird, you can go ahead and get the worm on the homework. You could solve all 3 problems tonight if you wanted. But we'll practice this some more on Friday. So I'll see you then.